Okay, this may be the end of this chapter only. So now we'll see how in uh, the cantilevered beam will work in this atomic force microscopy. So one, the cantilever beam deflection will affect the magnitude of the force, which will indirectly affect the image quality. So the force between the tip and the sample generates elastic bending of the cantilever, and the amount of bending is mounted and recorded by the position sensors, photodiodes, which are arranged in four quadrants. So the photodiodes are receives the laser beam. So they are sensors, they can detect the deflection of the cantilever beam. In other hand, the cantilever beams should be thin metal coated materials. So the making it a mirror surface, and any small deflection of the cantilever will tilt the laser beam to other direction. So you will get the distortion of the image of your atom surface. So the correct positioning of the cantilever should be there. The difference between the two photodiode signal indicates the amount of cantilever deflection. So the amount of deflection in turn can be mathematically converted into the force. So the magnitude of the force affects the quality of your image. So the other one is the cantilever beams have been used for detecting the deflection, interferometry, and the piezoelectric crystal materials. I told you the piezoelectric crystal material, any change in the magnitude of the voltage will create a deflection distance. So the photodiode arrangement, however, is most commonly used because it is an expensive one. There are two systems of this cantilever beam working, the single beam and the triangular beam here. These are the probe tips in atomic force microscope. The single beam one is this one, and this one is a single beam one also. This is when it is a triangular beam of the cantilever is applied. So the single beam cantilever beam usually made from silicon with a dimension of about maximum 500 micrometer long and 0.5 up to 5 micrometer wide. You see the probe tip, the cantilever beam tip is very, very small, micrometer. So how can we manufacture this? With precision advanced manufacturing instruments. Okay. So the probe will work in two systems, in two geometries, single beam and triangular beam. So the triangular beam is commonly made from silicon nitride, and the single one is made from silicon only. So most cantilevers are produced with integrated chips in a microfabrication process. You may have studied in precision manufacturing, similar to process for manufacturing integrated circuit types. So operational mode of atomic force microscopy. The operational mode here divided into static and dynamic. The static force and there's a dynamic force. We said it is different from scanning two-leading microscopy because the atomic force microscopy can measure the forces between the probe tip and the sample, isn't it? So these are the static and dynamic mode of operation we will see. How many mode of operation we have seen in scanning tunneling? 4. Constant current, constant height, and others. So this will work in static and dynamic mode. We will see. In the static mode, the cantilever statically deflects to a certain degree, and the feedback loop maintains the value of what? Deflection of the cantilever beam. So static mode measures the deflection, magnitude of the deflection, but the dynamic mode measures what? The frequency oscillation of the cantilever beam. Dynamic mode, the cantilever oscillates. It will not translate, or it cannot displacement, but the dynamic one measures the cantilever oscillation at the designated frequencies. So the control loop maintains a set value of amplitude of oscillation. Is it clear? Please have your own notes. The function of feedback loop for static mode and dynamic mode are different. What are these? The function of the feedback loop in controlling operational modes of atomic force microscopy in static and dynamic are different. So in static mode, the tip on the cantilever physically touches the surface to be examined. When in static mode, with the deflection, the control loop measures the deflection, it can touch the surface of our sample. Thus, the static mode must be a contact type. Static mode እና dynamic mode ልዩነቱ ምንድነው? Dynamic mode the cantilever oscillation frequency ነው measure የሚያደርገው. Okay? The static mode can measure the deflection on it, not oscillation. So static mode can measure only, it can work in contact type, the tip to surface. But the dynamic mode include both contact, non-contact, and intermittent also. ሶስት ነገር አለ። Dynamic, which oscillation measure የሚያደርገው, it can be contact, intermittent contact, or it can be non-contact. The intermittent contact one is called typically tapping mode. We will see that one. Zigale, we will see. Okay. The dynamic mode can work in three of these. It can work in contact mode. It can work, the probe can touch intermittently the sample surface, or it cannot totally touch also, non-contact mode. Whereas the static mode, the deflection of the cantilever, which is controlled by piezoelectric piezocrystal material, it work only in contact mode. So the difference between static and dynamic modes can be illustrated using the graph here. Here is a graphic, the force created by the cantilever beam and the distance between the probe tip and the sample is A here. So in A here, these are the surface atom of the probe tip from the cantilever beam. The below one is our sample. So they are in what? Non-contact. Here, a non-contact mode. So if you see the graph here, the non-contact force, the line, the visible line, and the surface atom forces, where the distance are moving apart from the probe tip, is a hidden line here. So still there is what? A distance here, a distance Z, which is a distance Z between the probe tip and the sample here. So we have seen the distance tip is inversely proportional to the force. So here in the graph 2, you will see a contact tip mode. Here the atoms of the two are in contact, as you see from the graph here. And the graph, the force to K, which is the cantilever spring constant, is the distance between the probe tip and the sample. So the force of the cantilever, which is generated due to the deflection caused by the change in the voltage over the spring constant, cantilever spring constant. So the solid line marks total force between the tip and the sample. The dashed line I thought marks short range forces and oscillating amplitude of the tip if it is a dynamic mode application. The arrow mark the jump in and of the spring of constant in static mode. So anyway, this will affect the quality of your sample or the quality of the image taken about the atoms at the surface. So mostly the contact mode cantilever beam is applicable in the atomic force microscopy. So the static contact mode, which is, it looks like this. The cantilever beam, the forces from the surface atoms, these are F repulsive force, F attractive force. We have seen the magnitude of F repulsive and F attractive will affected by the overlapping of the atoms. So if the overlapping atoms reduce, the force of attractive is high. So the force here is equals to Kn times change in the distance Z between the probe tip and the sample surface. So the attractive long range force attractive, are the balanced by the short range repulsive forces at the contact area and the spring force of the cantilever beam. Clear? ለምንድን ነው ፎር ካንቲሌቨር ቢሙ አፌክት የሚያደርጉት? ሰርፌስ አተሞቹ ዲስታንስ አለ and the biased voltage condition. እነኚህ ነገሮች አጀስት ካላደረግን ደግሞ we cannot have a good image of surface atom properties. Surface atom property ለምን እንደምንፈልግ I have explained before. So the tip apex is brought into the region of repulsive force while the rest of the tip experiences attraction to the sample. So the cantilever force proportion to the vertical deflection will balance with forces on the tip. So there is a surface atom forces, the repulsive, and the interaction like here we have seen. ሁለቱም ሰርፌስ አተሞች በገናኙ ይሳሳባሉ፣ ባይገናኙ ይሳሳባሉ። የሚሳሳቡበት የፎርስ በማግኒቲዩድ መካከል ያለው the quality of your image characterization determine ያደርጋል። So the dynamic operation mode which measures the oscillation frequency of the cantilever beam, dynamic mode. Dynamic operation mode በምን ይሰራል? በኮንታክትም non-contactum or intermittent or tapping contact. So the dynamic mode include non-contact, intermittent, and so on. So the dynamic contact mode is also called force modulation. And the dynamic non-contact mode is non-contact mode. The mode can provide true atomic resolution and image quality comparable to scanning tunneling microscopy. So dynamic non-contact type will give a good image comparable to tunneling microscopy. So the cantilever is excited by the piezo actuator. I told you find out what are the piezo materials particularly. And the vibrating tip is brought near a sample surface, but not touching the surface. You please write one note. The scanning tunneling microscopy will never ever use work in a vibration condition, but in atomic force microscopy, the probe tip itself can oscillate. So the frequency of oscillation should be controlled, which can work in contact mode, non-contact mode, or in intermittent tapping mode. To sense the weak attractive force between the tip and the sample instead of strong repulsive force in the contact mode. So the cantilever beam of the probe looks like this one. Okay, it can oscillating, then it can be here, it can be here, or it can be in between. It can oscillate up and down. So if you draw the graph, the frequency of it looks like this one. This is the current where the probe exists. This one is the trace back oscillation of the cantilever beam. So the dynamic non-contact mode, the frequency shift of the cantilever oscillation is used to operate the feedback loop. Feedback loop ለምን እንፈልጋለን? ይዛችሁ feedback loop is good for in dynamic state. ምን control ያደርጋል? ፍሪኩዌንሲውን ኮንትሮል ያደርጋል። የኦሲሌሽን ፍሪኩዌንሲን ኮንትሮል ያደርጋል። ኮንትሮል ካልሆነ ደግሞ it will not give a good image of the surface atoms. But the static gize, it will, the feedback loop controls the deflection. So the interaction force detected in non-contact mode provides excellent vertical resolution. So however, this mode can't be operated in liquid environments. Non-contact dynamic one will not work in liquid environment. Even in air, liquid attack on the tip can cause failure in operation. The other one, intermittent. When the cantilever beam is at intermittent, means once it touch and at very small frequency, it will leave the surface of the sample. What happened here? Like you see from this figure here, at the current position of the probe, cantilever beam is this one, the black one. It can be here, it can be there. So the role is you have to control the constant amplitude changes. Amplitude and the small and the high level. Oscillation amplitude should be maintained constant here. So this mode is intermittent contact mode in which the cantilever oscillates and brings the tip to light touch. Light touch. Then the surface to provide high resolution, and then it lifts tip off the surface to avoid the surface damage. So it is a tapping mode, one it touch and it will lift. The role is to control the frequency of the amplitude. The tapping mode here, the oscillation of cantilever is damped when the tip touches the sample surface at each cycle. So the image is formed by keeping the oscillation amplitude constant. What I told you before. The amplitude should be constant. So force modulation. Here, the force modulation is another operational mode in dynamic contact mode. So it will work on identifies and maps the difference between the surface stiffness and the elasticity. So this technique uses variety of surface properties to differentiate among materials where the topographical differences are small or not measurable. So here, the force modulation looks like here. The frequency of the cantilever beam. So we have to maintain the constant amplitude here, even if it is in tapping mode. The force modulation is therefore the cantilever deflection during scanning is recorded, and under the same applied force, the stiffer the area on the sample will undergo less elastic deformation than soft area. It is obvious our sample may not uniformly stiff, or at some areas the stiffness may vary. So the variation of the stiffness of surface atom will affect the probe tip here. Okay, the stiffer the area on the sample will undergo less elastic deformations than the soft area. It will deform more. It is obvious if it is. So force modulation, the tip is kept in contact with the sample. The difference in local property of the sample will be reflected in the amplitude change of the cantilever force. So force modulation is one in the dynamic contact mode. Typical application of this atomic force microscopy here. So the static contact mode is simplest method, I told you, to use for obtaining basic topographic information of surface atom, solid surfaces. The contact mode was able to detect nanoscale roughness, the asperity at even nanoscale, surface atom defects, and the geometries, and also the crystal plane, crystallographic plane of the atom. It can tell you also this the defects here. So this is particular image taken from one published work, or from the book. You will see the contact mode was able to detect nanoscale roughness of crystalline polyethylene material, which is believed to be chain folds. So see how clear the surface looks like. It is up to 0.5 nanometer. በዚህ ናኖሜትር ሬንጅ ውስጥ ሰርፌስ አተሞቹ ምን አይነት አስፕሪቲ ኃይል Now the bonding structure they have, you can clearly observe here. So topographic of crystalline polyethylene example, the chain folds of the crystal structure generates the rough appearances here. 0.5 nanometer ማለት ራሱ very mirror surface ማለት but such magnifications in night we will look like here rough surface, very rough surface. The other one, dynamic non-contact modes. You will see such an image I have taken from one. The dynamic non-contact mode can provide atomic resolution in ultra-high vacuum, even though it is more difficult to generate an atomic image with atomic force microscopy. So a non-contact mode image of hydrogen terminated silicon. So here, the gap between atoms here, you see, 0.35 plus or minus 0.01 nanometer. They have measured such a way on the instrumentation itself during taking the image, you can see the spacing between here, the size of this atom here, like this person I have taken here, you see, the line arrangement. Is it clear? ግልጽ ነው ቢኒያም?
Yes, ግልጽ ነው።
So the image artifacts. So we are going to finish here. While the scanning probe microscopy offers unique advantage for surface measurement in terms of simplicity and high resolution, we can use two instrumentation, scanning tunneling, scanning tunneling microscopy and atomic force microscopy. So it is unique problem of image artifact caused by near field interaction between tip and the sample. So one drawback of this probe instrumentation is one, high surface finish of the probe material, which needs high technologies. And the other one is processing the sample itself. And the typical artifacts introduced from several sources are briefly described in this section, like this one, okay? The cantilever beam, either we can use triangular or we can use a single cantilever beam here. So you can read this one, vibration and operation. We said the scanning tunneling microscopy will not work in vibration condition. Atomic force microscopy will work in oscillation of the cantilever beam. In controlling the oscillation frequency of cantilever is very important. This thing you have to cover yourself. So thank you very much. This is the end of this chapter only. We have another PowerPoint also, which later next week maybe we can complete this course. Any question? ጥያቄ አለ ቢኒ ዮሴፍ? ዋንሲኒን ቀለው ጅራት. And I will give you the video, the 3 videos recorded here now itself. And your Telegram, you contact me, I will give you your mid-exam points, and we will discuss on Telegram individually.
Okay.
Good to know?
Yeah, doctor.
Okay. You can see the video, I will give you the PowerPoint, and you can browse additional material and see and develop your skill on using this instrumentation.
Okay.
Thank you very much.
Thank you.